An electron moves in a circle of radius r around a very long, uniformly charged wire in a vacuum chamber, as shown in the figure. The charge density on the wire is lambda equals 0.21 microcoulombs per meter. What is the electric field at the electron, magnitude and direction in terms of r and lambda, and what is the speed of the electron? This problem is a book problem that comes from chapter 21 of the textbook. However, the solution for the electric field is much easier using the techniques of chapter 22, i.e. Gauss' law. And so for this video, since it will be used to study for the exam and all of this information will be available at that time, I'm going to solve for the electric field using Gauss' law. When one uses Gauss' law, the technique is to select some point near the wire. Let's say this point is an example. And then imagine in your mind the collection of all points that have exactly the same electric field as that point. Well, we can imagine a circle that is centered around the wire itself. The electric field should be the same in all locations along that circle. We can also imagine that as this circle slides along the length of the wire, we again have the electric field the same at all locations. Now, we should never attempt to encompass the entirety of an infinitely long wire, then all of the terms in Gauss' law will be infinity. So for that reason, we're going to cut off this cylinder that surrounds the wire, and we're going to do so with some length that we will call L. Obviously, L is a variable that we invented for the purpose of solving the problem. The electric field in real life around a charged wire cannot possibly depend upon our choice of technique of how to find the answer. So our expectation is that by the time we have finished this application of Gauss' law, even though we have used L as a crutch to perform the calculation, the L will have dropped out before we're done. As you will remember, Gauss' law says that the closed surface integral of the electric field dotted with a differential area element dA is equal to the enclosed charge known as Qin divided by epsilon naught. Although this formula may seem daunting because of the inclusion of abstract mathematical symbols such as the closed surface integral, in fact, we will only solve a Gauss' law integral in those situations where we can do so advantageously. Advantageously means we are able to identify surfaces where the electric field is either perpendicular to the surface or parallel to the surface. In this case, our shape that we have made for our closed surface has three portions. It has end caps at each end, and it also has something that is shaped like a hollow cylinder, and we're going to call that the barrel. And we can see that in order to integrate over the entire surface, we're going to have three portions to this area integral. The end cap at the left end, which we can call 1, the end cap at the right end, which we can call 2, and the barrel. The dot product eliminates all terms for which the electric field vector is parallel to the surface. That means that both of the end caps in this sum will drop out and become 0. Because we have so carefully chosen our surface such that the electric field everywhere on this surface is a constant, it actually comes out of the integral, becoming E. And the integral of dA is simply A, the area of the surface. So, as with all Gauss' law applications, we have a dramatic simplification having chosen the one special surface for which the integral is trivial. EA is Qn over epsilon naught, and 2 steps remain in order to solve this problem and get the electric field. First, we must substitute something for the area of the barrel. We can see that the area of the barrel is going to be 2 pi r. That's the circumference of a circle times length. Always check your area formulas to make sure they have the right dimensions. They should be an area, length times length, not a volume, and so 2 pi r times L satisfies this condition. Second, we need to determine what is the Q in, and this is the charge enclosed. Now, not the entire infinitely long line of charge is enclosed by the Gaussian surface. Instead, merely a portion of length L is enclosed by our surface. Since we know in this problem lambda is the charge per unit length, we can take lambda as a charge per unit length and multiply this by the amount of length that we have taken in the interior of our Gaussian surface. Plugging in both of these formulas will allow us to solve for the electric field. In this case, we find that E times the area of 2 pi RL is equal to Q in, which is lambda over L divided by epsilon naught. The L's, as we had hoped, do cancel from this formula. That gives us confidence that we're doing this calculation correctly. And then we were able to solve rather simply to find the electric field. The result we get is 1 over 2 pi epsilon naught lambda over r. As we remember, 1 over 4 pi epsilon naught is the same thing as k. Well, this is not divided by 4, it's divided by 2, so it's twice as large as k. So this formula can be simplified to be twice the constant k lambda over r. And that's the answer for part A. For part B, we recognize that we have an application in which we are to find the speed of the electron. And looking at the figure, the electron is moving in uniform circular motion. As we remember from first semester physics, uniform circular motion is a force problem, and the first step in every force problem is to draw a free body diagram. So we will draw a free body diagram located at that point, and we ask ourselves to name any one force acting upon the electron at this point. The force that we know of will be the electric force, in that the electron is attracted to the wire. Previously in the problem, we solved for field, and what we remember is that force is equal to charge times field, where I'm going to write Q as the charge of the electron. Because the electron is so light, the gravity force is entirely negligible compared to the electric force, and this is the complete free body diagram. It is a one-dimensional free body diagram, and so we will pick the plus direction with that force, which is with the acceleration, and there is a name for that direction. The name for that direction is centripetal. Because we have a one-dimensional free body diagram, we will only be writing a single Newton's law equation. That will be for the centripetal direction. There is one and only one force in the centripetal direction. It's Q times the electric field. And as we know, the sum of forces is equal to m times a. And we have to ask ourselves, is there an acceleration in the centripetal direction? The answer to that question is always yes. So the ma term on the right-hand side of F equals ma has a mass of m and an acceleration v squared over r, the familiar result for any circular motion. At this point, we are able to plug in the formula, which is the result of our previous step, so that the electric field will be replaced by twice the constant k, lambda over r. That will be equal to mv squared over r, and we get a very beautiful cancellation because the variable r drops out from both sides of the equation. This then makes it very easy for us to solve for the velocity. The velocity will be equal to the square root of 2qk times lambda divided by the mass. Lambda has been given in the problem. K is the well-known constant, and in order to solve completely, we need to find the charge and the mass. Well, since we've been told that this is an electron, we look that up. The charge is 1.6 times 10 to the minus 19 coulombs. The mass is 9.1 times 10 to the minus 31 kilograms. And if we plug in all that information, we're going to find that the velocity of this electron is 25766,537 meters per second. You may be concerned at this point that that's a fairly high velocity, but in fact, I don't think so. It's actually less than 10% of the speed of light, and for an electron, that's not fast at all.